You probably remember learning about them in school. They feel totally solid, right? Like the ground beneath our feet. I'm talking about scientific laws. But for this explainer, we're going to pull back the curtain and ask a simple question. What is a scientific law, really? Yeah, we tend to think of science as this vault of absolute truths. And the crown jewels in that vault are the laws. Newton's laws, the laws of thermodynamics. They feel like the universe's fundamental rulebook, the very code that lets us do incredible things like land rovers on Mars. They just feel like the truth. But here it is, the big question that's going to guide our whole journey today. What if these laws aren't some kind of divine commandment etched into the fabric of reality? What if there's something way more human, more temporary, and honestly, a lot more interesting? What if they're not the final word? So to really dig into that, we've got to get on the same page. We need to agree on our terms. What does science actually mean when it uses the word law? Because trust me, how we define it changes pretty much everything. Okay, so here's the textbook definition. A scientific law is a statement that describes something we see happening over and over again. It basically sums up the results of countless experiments. But the key word here, the one I really want you to focus on, is describes. A law tells you what will happen, like an object in motion will stay in motion. It doesn't tell you why. And this is so important for clearing up a super common misconception. Let's break it down. A fact is just a basic observation. An apple falls. A law then describes how it falls, often with a neat little equation like F equals ma. But the theory is the big overarching explanation for why. Einstein's theory of relativity explains the why behind gravity. So you see, a theory doesn't grow up to become a law. They have two totally different but equally crucial jobs. And that leads us to this massive realization. Scientific laws are not forever. They're not written in stone. A law is true under a certain set of conditions. Take Newton's law of universal gravitation. It works perfectly for predicting how planets orbit the sun. I mean, perfectly. But when you zoom way down to the quantum level or get near something insanely massive like a black hole, it just falls apart. New evidence didn't prove Newton wrong. It just showed us the limits of his law. It restricted its domain. Okay, so if laws aren't these absolute truths handed down from the cosmos, then where do they come from? Well, they come from people. And the whole process is messy, it's full of arguments, and it's just a beautiful human story. Let's see how it works. We have this picture in our heads, right? A lone genius like Newton gets hit on the head with an apple, and boom, a law of nature just appears, fully formed. But the reality is nothing like that. It's much more like building a massive cathedral over many, many decades, with a bunch of different architects who are all arguing about the blueprints. To really see this in action, let's take a look at how the laws of thermodynamics came to be. So our story starts way back in 1824 with this French engineer, Sadi Carnot. Now, he wasn't trying to discover some fundamental secret of the universe. Nope. He was trying to solve a very practical problem: how to build better, more efficient steam engines. His ideas were brilliant, but they weren't math. He used this analogy of heat falling from hot to cold, just like water turning a water wheel. It was a killer insight, but it was just an idea. It wasn't a law. And this is where it gets really interesting, because it shows the next step. 10 years later, this other engineer, Émile Clapeyron, he takes Carnot's brilliant, but kind of fuzzy ideas and does something totally transformative. He translates them into the precise language of math. This plot you're looking at, it's a visual tool he invented to map out Carnot's cycle. He was giving mathematical muscle to what was once just an intuition. He was building on the foundation. And the story was far from over. For the next 50 years, giants like Clausius, Kelvin, and Maxwell all threw their hats in the ring. They argued, they ran experiments, they built on each other's work. The final laws that you might memorize for a test weren't just discovered in some flash of genius. They were constructed, they were fought over, and they were assembled piece by piece. A true monument to a messy, collaborative human process. So this all leads us to a much deeper, almost philosophical question. If these laws are human constructions, what exactly are we building them from? Are we just discovering a blueprint for the universe that was already there? Or are we actually inventing the blueprint itself? The answer might tell us more about our own minds than about the cosmos. Let's start with this quote because it is a real mind-bender. It's about the second law of thermodynamics. The idea that things always go from order to disorder. You know, a hot cup of coffee always cools down and never just spontaneously heats up. This arrow of time feels so fundamental. But what Yanofsky is saying here is radical. He's saying this irreversibility isn't a property of the universe. It's a result of our own ignorance. Because at the tiniest subatomic level, all interactions are perfectly reversible. It's only because we can't possibly track every single particle that a one-way law appears to us. Think about what that means. The law is a product of how we, as limited beings, have to filter information. We decide what to pay attention to and what to ignore as noise. We group things together based on patterns. We assume an experiment in London works the same as one in Tokyo. And from those choices, we create a law. The law feels objective and real because we literally designed it that way. It's a model shaped by the very limits of our minds. Now, to see how deep this rabbit hole goes, check out these diagrams from physicist Kevin Nuth. And don't worry, they look way more complicated than they are. All they're really showing is how basic logical ideas, like this is a part of that, or if X, then Y, create a predictable structure, a kind of grammar for relationships. And here is the big payoff. Knuth argues that the rules of math, like addition, aren't just random. They're what he calls constraint equations that basically enforce the logical grammar we just saw. So the reason math is so unreasonably effective at describing the universe might be because the laws of physics are just reflections of the logical structures we use to think in the first place. The laws work so well because they're built with the same logic that our minds use to make sense of anything. So our laws are these incredibly powerful, human-built tools that reflect the way our minds bring order to reality. But just like any tool, they have their limits. And it's right there at the breaking point where our laws fall apart that science gets really, really exciting. Okay, take a good, long look at this chart. This is our best guess at what the entire universe is made of. And honestly, it should be a little bit humbling. Everything we know, everything we have ever touched or seen, every star, every planet, you, me, all of it is made of what we call ordinary matter. And all of that stuff, it's just 5% of the cosmos. Let that sink in for a second. All of our beautiful, elegant, Nobel Prize-winning laws of physics, they only describe that tiny 5% sliver. They have basically nothing to say about the 27% that is dark matter or the absolutely mind-boggling 68% that is dark energy. Our universal laws aren't very universal at all, are they? They're more like local rules for our tiny corner of reality. But this isn't a downer. This isn't a story about failure. This is a story about opportunity. This huge landscape of what we don't know isn't a reason to give up on science. It's the entire reason science exists. This is the frontier. And here are just some of the questions that are keeping physicists up at night. How in the world do you build one theory that connects the world of the very, very big with the world of the very, very small? What is dark matter really? You know, answering any one of these questions is probably going to take a complete revolution in how we see things, and maybe even a whole new set of laws. I absolutely love this quote because it just perfectly nails the true spirit of science. The whole point isn't to get to some final, unquestionable truth. You know, certainty is boring. Certainty is the end of the road. It's admitting you don't know, being aware of the mystery. That's the engine that drives the whole thing forward. So, when you get right down to it, maybe we've been thinking about science all wrong. Its true strength isn't its encyclopedia of facts or its rulebook of laws. Its real power is in the method. It's a process for being wrong, for finding your mistakes, and for slowly, step by step, getting a little bit closer to a better description of how things work. It's a system built on doubt, not on faith. And that brings us right back to where we started, with a question. If our scientific laws are shaped by the very structure of our minds, our logic, our math, the way we filter reality, it leaves us with one final, kind of haunting thought. What truths about the universe might exist that we aren't just unaware of, but that we might be fundamentally incapable of even imagining?